Alrighty, we are starting a new chapter, chapter 8, bonding, the general concept. So we've gone over bonding before, very generally, and now we're going to look at it a little bit more in depth. Alright, let's look at this, the types of chemical bonds. So hopefully you remember a little bit about this from some of our first couple of chapters in this textbook, but we first understood bonds in chapter 2, and they are forces that hold groups of atoms together and make them function as a unit. So instead of being individual atoms, they now are forming as a new unit. And this can be observed by things like physical properties, melting point, hardness, conductivity, solubility characteristics, and the properties of solutions like that as well. So a chemical bond, things that have been chemically bonded, they will behave differently than individual atoms will. And we can obtain information about the strength of bonds by measuring the bond energy, or the energy required to break a bond. Okay, we've seen how sodium and chlorine atoms interact to create ions, sodium ions, the cation, and chlorine ions, the anion. And they form an ionic bond of sodium chloride. But why does this process occur, right? So we know that this is true, but why is it true? And why does it happen? Well, the best answer is that the system achieves the lowest possible energy by behaving this way. So nature is, in a way, it's lazy, just kind of like we are sometimes, where we're trying to do things that require the least amount of energy at some points in our lives. But nature does this as well, and so that actually is what creates bonds. The attraction of the oppositely charged ions when they've shifted that electron is very strong and results in a very sturdy material with a high melting point, sodium chloride. Ionic substances are formed when one atom that loses electrons relatively easily reacts with an atom that has a high affinity for electrons. So things that want to draw electrons will, and then they'll become attracted to one another because of the positivity of one and the negativity of another. So an ionic compound results when a metal reacts with a non-metal. So we've looked at this before as well, generally the left side of the periodic table that are metals, or the central portion, which are the transition metals. They react with the right side of the periodic table, which are the non-metals. The energy of this interaction can also be calculated using Coulomb's law in this form. Okay, so we've got this equation where E is energy in joules, and Q1 and Q2 are numerical ion charges. So for example, sodium would have a numerical ion charge of 1, while chlorine would have a charge of -1, and R is the distance between the ion centers. An example of Coulomb's law is sodium chloride, right? So here we get it, and R is usually going to be given to us, 0.276. So again, that's the distance between the ion centers, or their nuclei. Okay, so it's 0.276 nanometers, and we can plug that into the equation and find the energy required to break the bond. The negative sign indicates that the attractive force, meaning the ion pair has lower energy than separated ions. Okay, so ion pairs have a lower energy than the separated ions, which means they're going to actually bond to one another. This can be used for like ions as well. An example of this is hydrogen. So each atom repels the other because of the like charges, but there are conditions in which a bond between two atoms will form. A system is always trying to achieve, again, the lowest possible energy, so it will attempt to minimize the positive or repulsive energy term. So up here, this negative, that means there's very little energy required, right? So we're going to try to minimize positive energy terms, okay? In this following diagram, you can see that the energy terms are accounting for both the potential energy from attractions and repulsions and the kinetic energy due to the electron motion. And you can see that the potential energy grows towards zero as the internuclear distance increases. So as they get further and further apart, their potential energy gets smaller and smaller, right? So here we go. Tight atoms up right here. Those very tight hydrogen atoms are less likely to form because of the positivity of each nucleus pushing each other away. But then there's this specific distance where things are working really, really nicely for them. And so they will actually form, and then you get them closer to zero, closer to zero. So this little spot right here, when they're 0.074 nanometers apart, that's when hydrogen is most likely to bond with another hydrogen atom. So when the atoms are close together, the energy is very high because of those repulsive forces, so they're not likely to form. But the bond length that actually occurs is the distance at which the system has its minimum energy. So if we look back at that again, that 0.04 or 0.074, that is where it has its least amount of energy. And the reason that the bond occurs is because the electrons stay mostly between the two nuclei because of their attraction to protons in both of the nuclei. So rather than revolving on the outskirts of that hydrogen bond, those electrons actually hover kind of between the two nuclei. We can also think of this bond in terms of its forces. The proton in each nuclei pulls on the other hydrogen atom's electron and draws it in until the proton-proton positivity limit the closeness of the atom. So they draw closer and closer and closer because the electron is being pulled to the opposite proton until the proton is like, too close, and I'm going to start repelling again. Or the repelling force is just as great as the attraction of the proton to the electron. So this type of bonding where two nuclei share surrounding electrons is called covalent bonding. So it's not ionic any longer, it is actually covalent bonding. Okay, they're sharing electrons. And when two atoms in a covalent bond share electrons equally, we call them nonpolar covalent. So there are different types of covalent bonds as well. We've got polar and nonpolar. So when the two atoms are not so different as to exchange electrons, so metals and nonmetals, which is ionic bonding, but different enough not to share electrons equally, so they're not sharing electrons perfectly like hydrogen do. One has a greater pull. We call them polar covalent, greater pull, P-U-L-L. They're polar covalent bonds, okay? So we've got non-polar covalent bonds and polar covalent bonds. So an example of a polar covalent bond is hydrogen fluoride. We see the polarity when it's stimulated by an electric field, okay? So we look at how it reacts in an electric field. And this is totally in kind of building on top of chapter 7, where we talked a lot about electronegativity and the tendency for an atom to attract electrons as well, the electronegativity, right? So fluorine has a huge affinity for electrons, and so it will kind of pull on that electron a lot and cause a sort of imbalance, but it's not enough to where it will actually take the electrons totally away. So it won't become ionic, it will stay covalent, but it has the electrons most of the time. So here's the example that you can see. When we actually electrify the field that they're within, you get those little delta positives and delta negatives, all pointing in the same direction because of the electronegativity of hydrogen fluoride. It gets that partial negative charge. All right, section 8.2, electronegativity. Here we go. The concept of different affinities of atoms for each electron, for electrons in a bond can be described by a property called electronegativity, right? And we looked at this a little bit in chapter 7. We're going to look at it more now. So it's the ability of an atom in a molecule to attract shared electrons to itself. All right, and we use Linus Pauling's model to consider the hypothetical module of Hx. So this is just kind of a x here is a variable. So we calculate it first as if they will attract electrons equally, like this. All right, so this is what we would expect, is that they're going to just attract the electrons equally, right? So we're basically just averaging the bond energy. Okay, but then we find the actual measure and find the difference of the bond energies, that we could find the difference between the expected and actual. So it looks more like this, right? All right. So we're looking at the actual average, or the theoretical average over here, and then we look at the actual average that we discover down at the bottom. Okay. If we see the actual and the expected are the same, the delta is 0. So that delta on the bottom there, it would actually be 0. But if the X has greater electronegativity, then the shared electrons will be closer to the X atom, and the molecule will be polar with a charge distribution like this. Okay, so the thing that has the electrons more closely to it gets that delta negative, the X there gets the delta negative, and the H gets the delta positive. These polar covalent bonds are almost slightly ionic in nature, but they are still considered polar covalent. So while the electrons spend a lot more time by X, they're still considered polar covalent, not ionic, because they don't fully take that electron. And then the greater the difference between the actual and expected electronegativities of an atom, the greater the ionic properties. Okay, so the more similar it reacts like an ionic bond rather than a covalent bond. It basically essentially means it's just more polar. The electronegativities have been found for nearly every element, and they create another trend on the periodic table shown here. Okay, so fluorine up there in the top right, like we were talking about with hydrofluoric acid, HF, it's very, 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 very high, right? So it's 4, whereas H is 2.1. So fluorine just kind of naturally pulls on the electrons more. And as you can see, as you move toward the right on the periodic table, you grow electronegatively, and as you move down, you shrink electronegatively. Okay, so there's another trend on the periodic table that we observe. So as you saw, the range of electronegativity goes from 0.7 on the bottom left all the way to 4.0, okay? And the chart produces a helpful trend for the difference of electronegativities and the bond type that will be formed, okay? We can infer the bond type between two atoms by looking at their differences of electronegativity, right? We can figure out if it's going to be ionic, or if it will be polar covalent, or if it will be just covalent, non-polar covalent, okay? So here you see those types, right? If the electronegativity differences in the bonding atoms is 0, then we'll get covalent, okay? So if it's 0, you get covalent, and they have covalent characteristics. And then you kind of are on this sliding scale down to intermediate, where you'll have polar covalent, and then if the differences between those two values are large, then you'll get an ionic bond, okay? So if we look back here, on the left side, all these metals are fairly low, where all these non-metals are relatively high. So that's why we end up getting ionic bonds, because of those great differences in electronegativity. All right. Then we get bond polarity and dipole movements. So these are some new or dipole movements are new for sure. But you see how hydrofluoric acid reorients the molecule when it's placed in the electric field, right? The negative ends of fluorine kind of were drawn toward the positivity of the electric field, and vice versa for the positive ends. And this is because of those positive and negative ends, right? It's said to be dipolar, or having a dipolar movement, if it's represented like this. Okay, so the positive side is on the left, and we've represented it before with that delta plus, but now we're going to represent it with this kind of cross thing, with the arrow pointing toward the negative dipole movement, and this plus sign over here is the positive side. Actually, let's look at this graphic a little bit more. This is also kind of a helpful representation of where electrons spend their time too. So electrons spend a lot of time right around this fluorine's nucleus, whereas they spend less time over here around hydrogens, right? And that's due to the difference of protons in the nucleus as well. Another way to represent this is with an electrostatic potential diagram. Red indicates the most electron-rich region, and blue indicates the most electron poor region. So naturally, any diatomic or two-atom molecule, right, breaking that apart, di means two and atomic means atom. The molecule that has a polar bond will have a dipole movement, or two poles, right? A pole on either end. You have a negative pole and a positive pole, kind of like the Earth, right? The North and the South Pole. But some polyatomic ions can also exhibit this behavior. So polyatomic meaning many atoms, right? Sometimes they will also have a dipole movement. So water and ammonia are actually perfect examples of polyatomic atoms having a dipole movement. Because of how great the oxygen atom and the nitrogen atom's electronegativity are, respectively. So we've got H2O here, where oxygen has a really great affinity for electrons, but hydrogen's is much less. And so we actually get delta. Hydrogen has these two delta positives over here, and then oxygen has one delta negative. But notice that the sum of the charge really acts like this. It's not like we're pulling this direction and this direction. It's actually, the positivity is going directly to the left. So we represent that with the capital delta here, and the capital delta negative here. So we're representing all of those partial negative and partial positive charges by this sum of partial negativity here pulling to the right and partial positivity pulling to the left. Okay, and then you can also see this electron diagram as well, where electrons spend a bunch of time over here and then they spend much less time on the outskirts over here. Okay. So there's an example of a polyatomic dipole movement. And then we also have NH3 here, which really acts similarly with nitrogen's affinity for electrons. So those electrons spend a lot of time around this nitrogen and much less time around these hydrogens, right? And again, even though it's three-dimensional and we've got all these different poles in those directions, we still account this net pull to be directly downward and directly upward, okay, not in all these three directions, okay. All right, now because of carbon dioxide's linear shape, it does not have dipole movement. So even though the carbon has a much greater affinity, the oxygens have a much greater affinity for those electrons than does carbon, they're pulling in opposite directions, and so it actually never has a dipole movement.